Yeah, so I brought my laptop down to see that it's working. So we have to use the microphone to get it on the YouTube. And we'll switch between start off of just keep plugging away, and if there's those graphs that I have in the other one, I'll sit back here if you want to switch. The other one, or whatever your question is. Randy? Kevin, this is Andy Benson, farmer in southern part of the
I have, if it matters, I have brand new wells drilled, like my house, my new house. Neither of them have any chance of any surface.
I think we got decent coverage in the
I had signed up earlier, but by the time you guys got around getting samples, I'd already destroyed the well that I wanted to have. The new house went right over the top of it, so we already had bentonite down to.
So you're moving in the new one.
Whenever they get down to Pumpkin Rock, they're putting tile floors down now, so we're supposed to. Hanging cabinets, tile floors are going down, and just a lot of finish.
Yeah, that's one thing that we'll talk about.
What I was really curious about would have been fun to do is water out of the old well, water out of the new well.
Oh,
That would have been fun because they're in different
yep.
depths.
Big difference. Depth and the AC and all that stuff.
That's part of the reason we put a new well in that home. We knew it was compromised, but every time we had a spring thaw or heavy rain, sand and water. We knew that. We knew that there was wash going through that casing.
Oh, we'll stand up. We'll stand up. Okay. That'll work on this.
So we could just take this.
Oh, yeah. Yeah. We got 8 people watching. Three. Yeah, I graduated on Sunday and took a gap day on Monday and started on Tuesday. Some kids take a gap year, go to Europe. I took a gap day. $8.20 an hour I was making. Let's see, what do you got over there? This is for this. Yeah. Yeah. And then I'll dim these. All right, good evening. Can you guys hear me? So, no. Okay. Oh, the microphone said it's on. Let's see here. Oh, now you can? I just got to hold the microphone up to my mouth, of all things. Yeah, so good evening. Thank you for coming here. I'm Tyler Gutzmacher, County Conservationist. We're going to be going through the preliminary results from our groundwater study that we did in 2022 and 2023. Just out of curiosity, how many people participated in that? Great. Yeah, so thank you very much. Without that participation, we couldn't do a study. I was at the Red Cedar Basin Conference today, and counterpart from Chippewa County was talking about it, said, you know, surface water is easy. We want to take a sample out of the Red Cedar River. We drive over to the Red Cedar River. We take a sample and send it to the lab. Well, for a study like this, we need the public's participation. And so thank you very much for participating in this. So our main presenter is Kevin Masaryk. He's the groundwater education specialist at the Center for Watershed Science and Education, which is at University of Wisconsin-Stevens Point. And Kevin basically is making the rounds. Is there a county that you haven't given a presentation on groundwater yet in the state, or?
Quite a few. More counties.
Yeah, so it's groundwater has become a big topic in the state. People are asking the same questions everywhere. And so testing like this allows us to answer some of those questions. So I will turn that over to Kevin right now. And what we'll do is we're with it on YouTube. We will switch over to that view for them at home.
Thanks, Tyler, and thanks everyone for showing up today. But more importantly, thanks for participating for those of you that submitted samples. As Tyler mentioned, I work for University of Wisconsin-Madison Division of Extension, but also the UW-Stevens Point College of Natural Resources. So we partnered with Bering County back in 2022, or I should say 2022 and 2023, with the goal of sampling 800 private wells throughout Bering County. The goals of these programs really are twofold. So tonight, what I hope to accomplish is, one, provide some perspective for those of you that participated in terms of what those individual test results mean. We want to make sure that you feel comfortable understanding those numbers. But by testing as a large group or community, as Bering County has done, we get kind of a baseline or a snapshot in time of groundwater quality that we can use to help educate people about the connection of land use or geology to the water that's coming out of their pipes at home. So this, again, we're providing a little bit of education on drinking water quality, but we're also providing an overview of the Bering County well water testing. This should be of value both to the study participants and non-study participants. We want to make sure that you walk out of here understanding more about your water than you did when you arrived. Just helping you understand or see where the samples came from. So what we're looking at here, and would you mind dimming the lights a little bit? Yeah. What we're looking at here is a map of Bering County, helping us better understand where those samples actually came from. So anywhere where there's a number, that's a quarter section, a 40-acre kind of grid cell where we received a sample. If you see a number 2, in some cases I see 3s or 4s, That means we receive multiple samples from that same area. We want to provide enough detail to help you understand how water quality varies throughout the county, but not enough detail that you could identify any one individual well or parcel. My goals for today are just to help you better understand where your drinking water actually comes from. We'll talk about well construction and the ways in which well construction can influence water quality. We'll go through some of the individual test results, highlighting general groundwater quality. And then lastly, if there are things that are objectionable, either from a health standpoint or maybe in an aesthetic standpoint, we want to make sure you understand what those next steps might be. So I'll stick around as long as I need to after the program if people have specific questions. I'll also provide my contact information, my email, my phone number, in case you think of something after tonight's presentation. Getting everybody on the same page as to where your well water actually comes from. Your well water is groundwater. It's not an underground lake. It's not an underground river. It's just the water that occupies the empty space in the soil and the rock below our feet. It gets there as rain or snowfall, or snow melt, I should say. Groundwater is occupying the empty space in the cracks or fractures of the geologic materials below our feet. And groundwater is also always moving very slowly through those spaces in the sandstone, maybe the sand and gravel aquifers, and it's moving to nearby discharge features. So those would be lakes, rivers, streams, or wetlands. Anywhere where the water table is the top of our groundwater, anywhere where that water table intersects the land surface is typically where we're gonna find lakes, rivers, streams, and wetlands. And that's the final destination for our groundwater, unless a private well intercepts that water first. Most private wells are accessing water that probably recharged within a quarter, a half, maybe a mile or two of the well. It's not coming from Canada. It's not coming from Lake Superior. It's a very local resource. And anything that we do locally on the land surface has the potential to influence that, as do the different materials that water has to flow through in the soils or the geology below our feet. Watersheds are what we use to help define or understand the direction of groundwater flow. So just as water runs off over the land surface, there's changes in elevation of that groundwater table that help us understand how groundwater moves below our feet. It doesn't follow exactly surface water topography or the surface water flow, but oftentimes the surface water boundaries, the watershed boundaries at the land surface can give us some idea of how the groundwater is flowing beneath our feet. Those dashed lines that you see represent watershed boundaries. So any water that falls within those boundaries is trying to find its way to that river or stream that's contained within that watershed boundary. So the arrows, they're not exactly correct in terms of groundwater flow, but they give us some idea of the direction and maybe the amount of time that water is in the ground before it discharges at a river or a stream. And you can see the other thing to highlight is that it doesn't all flow in one direction. A lot of people assume that all groundwater flows from north to south, and groundwater just follows the elevation of the water table and actually can flow in any direction as you see on this map. Our groundwater is stored in different aquifers. Wisconsin has this layered cake geology where the lowermost bedrock layer that we'd encounter is what we call crystalline rock. Crystalline rock, think of a granite countertop. If you think of how much water your granite countertop holds, virtually none. Granite is not a good aquifer. It doesn't hold or store a lot of water. We actually think of it as kind of our basement or our foundation. Wisconsin's groundwater sits in those geologic layers that exist on top of the crystalline bedrock. So if you're drilling a well and you hit that crystalline bedrock, drilling deeper isn't going to give you access to an underground water source. Sometimes wells do have to be drilled into the crystalline rock, but it's usually as a last resort. Fortunately, in this part of the state, we have abundant supplies of sandstone or sand and gravel deposits left behind by the glaciers. And those are generally speaking going to be the primary aquifers for people in Bering County. Why we care so much about the geology is that the geology determines things like how quickly groundwater moves or how easily groundwater becomes contaminated. If we're talking about groundwater flowing through large cracks or fractures, there's less filtering going on. It's going to move much quicker, maybe tens or even hundreds of feet per day, whereas water moving through sandstone or sand and gravel aquifers might be moving a foot per day. So the geology is really critical for understanding some key things in terms of groundwater flow and groundwater contamination. This map just highlights the uppermost bedrock units that we'd encounter. If we scraped away the sand and gravel that was left behind by the glaciers, we'd see Cambrian sandstone in most of the county, with the exception of the upper northeast, where we have this outcrop of quartzite. And what did you call it, Tyler? You called it the Blue Hills?
Yeah, Blue Hills.
So the Blue Hills, and I definitely should switch the colors for the quartzite and the sandstone to reflect the Blue Hills on this map. But if you're well, and we'll see on a couple slides that'll come up in a little bit, the depth of the sand and gravel materials. If we scrape away those unconsolidated materials, this is the bedrock that we'd find. But in most of the county, we have abundant supplies of sand and gravel or other materials left behind by the glaciers that is going to provide an excellent water source. So in the northern portion, you'll see the dark green. Those are areas where we have more than 100 feet, different sands, gravels, glacial tills that's storing or holding some water. And then we have that sandstone layer beneath it. You'll notice in the southern portion, the areas in red or orange, those are the areas with a lot of hills, where on top of those hills, we just don't have a lot of soil or other sediment before we encounter that sandstone rock. So pay attention to this map. Keep this map in your head, because it's going to be very important when we start looking at some of the water quality results for the different parameters that we tested for. The soils are also really important. The soils act like the skin on our bodies. So the skin on our bodies helps prevent infection. It keeps bacteria and other pathogens from getting inside into our bloodstream. The soil is similar in that it's the first line of defense for our groundwater. It provides some filtering ability in the event that we have contamination from different chemicals or different pathogens or bacteria. It's got some filtering ability for certain contaminants. For other contaminants that dissolve in water very easily, the soil might not be able to adequately filter them. In areas where we have excessively drained soils, where the water infiltrates easily, we'd expect to also allow things like nitrate or pesticides to soak into the ground much easier as well. Most people in this room, if you tested in the program, you have what we call a private well. We have public wells, we have private wells. If you're on a public water system, those water supplies, you pay a water utility bill that supports a staff, it supports infrastructure. There's staff that are routinely testing that water. And if it doesn't meet standards, they're required to treat that water to ensure that it's safe for distribution to their clients. There's rules and regulations that public water systems have to comply with that ensures a certain degree of safety for anybody in that municipality who's served by that utility. Private wells, on the other hand, are not required to be regularly tested. So the fact that you participated in this program was strictly voluntary. It's a great opportunity to learn more about your water, but it's not required to routinely test. If we noticed anything wrong or objectionable, with your water, you're not required to take any sort of corrective action. We want to provide you with the information on what those corrective next steps might be, but we're not going to follow up with you to make sure you did X, Y, or Z. We want to empower you to have that information and make the correct decision for yourselves and your families. So if you take nothing else out of today's presentation, what I hope you'll remember is that you as a private well owner are kind of your own water utility manager, responsible for those decisions on when, what to test for, and what to do if there's an issue or problem. We did not test for bacteria in this program. It wasn't feasible with the sampling strategy that we put into place. But bacteria is an important test to do because it tells us about the sanitary integrity of the well water system. And there's just some slides I'd like to highlight because these are simple things that every homeowner can look for and correct to ensure they're giving themselves the best chance at getting bacteria-free water. So these are some common defects. Is the well cap casing or cracked? Anytime it rains, it's the fall, so there might be rain or leaves dropping in that casing, carrying with them bacteria. It's also an open hole into that well where as the temperature drops, you might have insects or even small rodents that are seeking shelter and might accidentally fall into that well. These are all things that are easily avoided by fixing that type of defect. Wells should have what we call a vermin-proof cap. So the picture on the top is showing a well that the cap was not on securely. When they lifted that cap off, they found a bunch of earwigs crawling around the inside. And if the earwigs are in there, a lot of times they might fall down into the water column. Vermin-proof caps provide a good seal. They have a fine screen that allows airflow, but it keeps unwanted insects or animals from entering that casing and contaminating our water supply. Other pitfalls to avoid, the electrical conduit. Again, vermin-proof caps are really good for allowing the electrical materials to be installed properly. We don't necessarily want to encourage our pets from spending a lot of time within close proximity of our drinking water. And then look at any bird feeders or other decorations around the well. Anything that encourages wildlife or provides cover for wildlife might provide an attractive environment, and we don't necessarily want to encourage them from spending a lot of time around our drinking water source. And then rural properties, a lot of times we'll have old wells, maybe old dug wells, that represent direct conduits into the groundwater aquifer. So this is a pretty extreme example of an old dug well. But you can see from the graphic on the lower left, if that old dug well is not properly filled and sealed, we might have rain or snowmelt that finds its way into that well that's directly injected into the aquifer, where we might have our new well where we're trying to get safe water from. So filling and sealing old unused wells prevents contamination from continuing to contaminate our water supply. Yard hydrants, livestock waters, service to outbuildings. We oftentimes don't necessarily think about this, but if they don't have proper backflow prevention, we might be using a yard hydrant with a hose. The water comes out of the yard hydrant, but when we turn that yard hydrant off, any water in that hose has the potential to be back siphoned into the well. And hoses are kind of breeding grounds for bacteria. So again, any livestock waters, yard hydrants, outbuildings, we want them to have proper backflow prevention so they don't contaminate our drinking water source. What makes a good well? A vermin-proof cap. Casing extends 12 inches at least above grade. Keep it free and clear of debris and other obstructions. And make sure that downspouts or runoff off of parking lots or driveways is not directed towards the well. I want to transition into the chemistry or the actual water quality results. And I just like to point out that we call water the universal solvent. As much as we all want pure drinking water, in the environment, we're never going to find pure H2O. So just because we find impurities dissolved in our water, it doesn't necessarily mean that water is unsafe to drink. there's certain impurities, things like calcium and magnesium, that come from the rocks or the soils that water moves through, that might actually be beneficial to health. There's other things like nitrate or chloride related to land use, which help us understand the degree to which land use activities are impacting our water supply. And some of those also have some health considerations associated with them. Even the plumbing and packaging that water is stored or transported in will impart different impurities. So if I were to say Flint, Michigan, what is the first thing that often comes to mind? Lead. So that's a pretty tragic example of a community that switched water sources from one water source to another water source that was more corrosive. The city or the municipality did not add the right anti-corrosion agents, and that water started to peel away at the scale, exposing heavy metals and other materials that had accumulated in that plumbing system over many years. And it was late in the game when they realized the detriment that they did to a lot of people that lived in Flint, Michigan. If we do have things in our water, some people probably received results indicating one or more things objectionable from a health or aesthetic issue. Just know that treatment oftentimes is a very effective mechanism for ensuring that the water is safer or more aesthetically pleasing. Not all of the tests that we did were important to health. There certainly are a number of them that have health implications, but just know that not all of them have health concerns. Some we do because they help us better understand the taste, color, or odor, or in the case of something like the saturation index, it tells us how is that water going to interact with our plumbing system. There are two different categories of health concerns associated with our water. There's acute effects. These are seen within a very short time after exposure, things like bacteria, viral contamination, where shortly after ingesting some sort of contaminant or pathogen, maybe a couple days after, maybe even a couple hours after ingesting some sort of pathogen, we develop symptoms, usually some sort of gastrointestinal symptoms. And then we have this category called chronic health effects, which result from exposure to a substance over a long or extended period of time. So if we find things like arsenic or pesticides in our water, drinking the water once or twice isn't likely to develop or result in any health complications. But arsenic or pesticides at certain levels, if that's our primary drinking water supply for years or decades while we're in the home, then we're at an increased risk of developing health complications later in life from that environmental exposure. Just because we find these things even at elevated levels does not guarantee that we're gonna suffer or end up having that health complication, right? It does increase the risk. Drinking water quality is only one of many risks that we all face. So how do we put this information into context? If we look at 1,000 people exposed to the different environmental conditions that we see, what are the odds of suffering some sort of consequence from that exposure? So all of us, 1,000 people, there's a 0.16 chance that any of those 1,000 people would be struck by lightning at some point in their life. If we look at indoor radon combined with smoking, 1,000 people exposed to those environmental conditions, we might expect 32 out of 1,000 to develop lung cancer from that exposure. Arsenic in drinking water, the drinking water standard's 0.01 milligrams per liter. 1,000 people drinking or using that as their primary water source, we might expect 3 out of 1,000 to develop some sort of cancer from that environmental exposure. Some people might look at 3 in 1,000 and say, that's a pretty small risk. I'm not that concerned. Other people might look at 3 in 1,000 and say, it's worth it to me and my family to purchase an RO system to reduce or remove that arsenic that would lower those odds to, less than 1 or 0 if possible. So drinking water standards, these are what municipalities use to decide whether or not they treat their water. Again, they're mandated to do that. but we use those same standards to provide some guidance to private well owners like yourself to help understand whether there's a need for additional measures or treatment. The tests that we offered, again, some of them are related to land use impacts, such as nitrate and chloride. There's others that we're going to go through because they help us understand a little bit about how geology or soils are influencing water quality and differences that people might be seeing. So starting with total hardness, this is measuring the amount of calcium and magnesium. It's naturally occurring. Some rocks contain more calcium and magnesium than others. A little bit of calcium and magnesium is actually probably beneficial to health. So no drinking water concerns when it comes to hardness, but too much can cause some aesthetic issues like scale formation, lime deposits on dishes. There might be scale on hot water heaters, especially electric hot water heater heating coils that cause an insulation-like effect where that water heater has to work harder to heat water to the desired temperature. So when water gets above 200 milligrams per liter, water softening is usually the type of treatment that people might pursue. If there's too little hardness, we have the opposite impact where we don't have scale forming. That water is going to be much more likely to corrode plumbing. Too little hardness means that that water is going to be more aggressive, particularly to the metal components in plumbing systems. So in the case of too little hardness or corrosive water, acid neutralizers are usually the treatment system that people would pursue to counteract some of the negative effects such as pitting or corrosion of copper plumbing or other types of metal fixtures. Acid neutralizers, if people have plastic or PEX plumbing, plastic or PEX is resistant to the corrosive nature of that water. So that is another appropriate solution to counteract the negative impacts of too little hardness or aggressive water. This map here shows what we found. In the upper left is the breakdown for the different concentrations. So we said anything above 200 milligrams per liter might warrant a water softener. That's only about 8 to 9% of the 723 water samples that would, based on the results, really need a water softener. So water softeners are going to be much less common in this part of the state than they would in, let's say, eastern Wisconsin, where they have a completely different geology and hardness levels, not unusual for them to range 300, 400, even 500 milligrams per liter in some extreme cases. The hardness, you'll see the darker, a little counterintuitive, the darker colors represent lower hardness values. So the water does get harder as you go towards the western edge, particularly the southwestern edge. That lower left edge of Barron County is an area where we start seeing the hardness levels increasing slightly. I mentioned water softeners. This is what some people will use to treat for hardness. Some people may have a water softener to treat for iron as well. Water softeners aren't designed necessarily to remove iron, but they do have some capability to reduce iron levels. pH is a measure of water acidity. Levels less than 7 are more likely to cause corrosion. So areas with low hardness values oftentimes have low pH values. Typical pH in Wisconsin is usually between about 6 and 9. In most of Wisconsin, it's going to be greater than 7, but too little causes corrosion. Blue-green staining is pretty good evidence of copper corrosion of plumbing systems. If we look at the pH, it mimics pretty closely the hardness values to where the river valley where we're looking at a lot of the sand and gravel deposits, we typically will see lower levels of pH. So pHs less than 6.5 are kind of unusual for Wisconsin. It's not to say that there's anything wrong with the water if it's got less than 6.5 pH. That's likely due to naturally low levels of calcium and magnesium in the aquifer. But it is something that might help explain why you have blue-green staining, why you have pitting or pinhole leaks if you have copper plumbing, or why you are going through more water heaters than people that live in other parts of Wisconsin. It may just be related to the low pH and aggressive nature of water in this region. Other tests, alkalinity, conductivity, and pH. We stick into what we call the saturation index. We use those other tests to help us calculate this index. Positive values mean scale formation. Negative values mean corrosion. The more negative, the more corrosive water is likely to be. Another thing that we looked for was manganese, and people might look at manganese and say, I've never really heard of that. What is it? Manganese is an element that, like iron, will occur more frequently in wells with low oxygen. Wells with low oxygen are going to be more common in areas with heavier textured soils. High water tables, so around lakes or wetlands, are areas where we may see more incidences of things like iron and manganese. Iron causes red or brown staining. Manganese is going to cause a black or gray staining. So the toilet tank you're looking at, there's black fine precipitate in the bottom of that toilet tank, and that's a telltale sign of manganese in the water. Aesthetic levels are going to be observable when the concentration of manganese gets to be about 0.05 or greater. And when the water reaches 0.3 milligrams per liter or more, then there's some health concerns associated with it. Nervous system disorders, people often refer to Parkinson-like symptoms as one consequence of too much manganese in their drinking water. This shows the extent of manganese concentrations that we found. So about 11%, just over 1 in 10 wells that we sampled in this program contained what we would assume are unsafe levels of manganese, and virtually 20% would probably have some evidence of aesthetic concerns associated with this element. Manganese is going to be more likely in that northwest quadrant of Barron County, in the part where we have the heavier ground because we have glacial till. We might have more wetlands. We might have more lakes in that region. Those are areas where we're going to see a little bit more or a little higher frequency of manganese in well water. Iron, I mentioned, often occurs simultaneously or co-occurs with manganese, also naturally occurring. There's no health standard associated with iron, but aesthetic, staining, taste issues are going to be more likely when that water has more than 0.3 milligrams per liter. Treatment for both iron and manganese would usually be some sort of oxidation or iron filter. Water softeners, again, can remove iron and manganese, but they're not really designed specifically for that. So if you don't need a water softener, if your water's not hard, then an iron filter and an oxidation filter is probably going to be a more appropriate solution if you're dealing with iron or manganese. This shows the iron concentrations. So we said 0.3 is the aesthetic cutoff. That's 7.3. It's about 12% of all the well samples submitted are showing some taste or staining issues associated with high iron. And the pattern is fairly similar to what we see with respect to the manganese levels. Arsenic is something that every well should be tested for at least once. The map you see on the right is showing what we knew about arsenic about 10 years ago. So any of the white areas are areas where we didn't have sufficient data to provide the average concentration in that grid cell. If we were to redo this map, Barron County would essentially be completely filled in. The good news from this information is that arsenic doesn't appear to be a large or major concern in this situation or this setting. 97% were undetectable, less than 0.005 milligrams per liter or 5 parts per billion. There were 3% of the samples that detected some level of arsenic, but those levels were lower than what's considered safe for drinking. So good news is that arsenic doesn't appear to be a major concern in Barron County. Phosphorus is not something that is an issue for health or drinking water, but many of you may know that phosphorus supplied to surface waters can increase the potential for eutrophication or algae growth. It's a limiting nutrient in aquatic systems. So as we add phosphorus, it increases the potential for algal blooms, potentially even harmful blue-green algal blooms like you see in the picture from Tainter Lake. Usually we associate phosphorus with soil or fertilizer runoff over the land surface. Phosphorus in groundwater is typically low, with the exception of places like Barron, Chippewa, parts of Dunn County. There's naturally elevated phosphorus in some of the bedrock units that we find here. Mainly, we call them Tunnel City, Wanawalk formations, the sandstone hills that we see in that southern area where we saw the shallow soils or those outcrops correlate really well with where we see elevated phosphorus. So rivers and streams that pass through these regions have a lot more evidence of phosphorus elevation that appears to be mostly naturally occurring. Doesn't mean we shouldn't be concerned about runoff from soils or erosion of soils, but it's going to be much more critical or important to limit those activities or limit how much runs off the surface because of how much exists in the groundwater already. And if phosphorus isn't the limiting nutrient in rivers and streams, then nitrogen becomes a limiting nutrient, and there's other issues with how much nitrate we're exporting to surface waters, and we'll talk about nitrate in a little bit. Nitrate and chloride are what we're going to talk about next. These are related to the land use or things that we do on the land surface. Chloride, naturally, we would expect levels to be less than 10 milligrams per liter. So if they're greater than that, it's usually an indication of fertilizer activity. So potash, potassium chloride that we supply to agricultural fields. The plants need the potassium, but the chloride dissolves in the water and leaches into our groundwater. Septic system effluent, so human waste, all of the salt that we eat in our diets, we excrete most of that out, which goes to the drain field. If we have a water softener, that's an additional increase of chloride exported to the septic system. And then also road salting activities, the de-icing that we do in winter. When that gets into the roads, the sides of the roads as the snow melts, that's going to soak into the ground and eventually reach groundwater. There's no health issues with chloride, but it can cause a salty taste when levels of chloride exceed 250 milligrams per liter. And additional salt, just like road salt will corrode your car, I mean, now we have better paint, better materials, so we don't see as much rusting as you might have seen back in the 80s or 70s. But road salt definitely will speed up corrosion of metal materials, including plumbing. If we look at the chloride levels, less than 10, about 60% of the well samples submitted show background or natural levels of chloride. So roughly 40% exceed that. There's a small number that are kind of high. It's not unusual to see the highest concentrations next to the more urban areas, next to major roadways, maybe intersections that get a lot of winter de-icing or road salt. Not unusual to see some of the highest concentrations next to those types of land use activities. The next thing I'd like to highlight is nitrate. So this is probably the most we do think of it as the most widespread groundwater contaminant. And it's the one parameter that we probably also have the most data on. It does have health considerations, which make it important to test for on a routine or frequent basis. Health effects, methemoglobinemia is a condition that can be fatal in infants if left untreated. High levels have been linked to birth defects and miscarriages, not only in humans, but also in livestock. So for those reasons, we don't want infants or women who may become pregnant drinking water with more than 10 milligrams per liter of nitrate. Increasing research is coming out to show linkages of nitrate to things like thyroid function or various types of cancer. So for those reasons, we'd encourage everyone to avoid long-term consumption of nitrate more than 10. Nitrate moves very easily through the soils. So if we consider the sources, fertilizers, septic systems, animal wastes, we might be concerned about other pollutants, things like pesticides, viruses, personal care products, things that are associated with the various sources of nitrate to groundwater. Naturally, we'd expect nitrate levels, if humans weren't here, we'd expect nitrate levels to be less than 1 milligram per liter. And typically in forested areas with a lot of grasslands, those are the levels that we typically would expect to see. If we do ever have elevated nitrate, drilling a new well could be an option. Sometimes drilling deeper gets you into older water that may be coming from a broader recharge area. So new wells sometimes may be an option. Otherwise, treatment for nitrate includes things like reverse osmosis, distillation, or anion exchange units. This shows the nitrate map. So nitrate, we said less than 1. We'll say less than 2 are kind of background or natural levels. That's about 50%. So not too far off from the chloride values. About 50% are showing natural or background levels of nitrate. If we look at the standard of 10, there's about 10% of wells that actually exceed that standard that we would essentially not want people to use for drinking and cooking. How does that compare to the state? It's right at kind of the statewide average. Roughly 1 in 10 wells statewide exceed that standard. So Bering County is very similar. But the thing that you're probably observing or noticing is that it's not distributed equally across Bering County. There's certain parts of the county that are going to be more susceptible or more vulnerable. If you're in that far northwest corner, that's an area where we just don't typically see a lot of nitrate. If you're in that central region or the river valley, those are areas that appear to be a little bit more likely to contain nitrate above 10. The dark red wells, any of them that are the dark red, those would be wells that exceed that standard. This just shows the distribution. So on the lower level, those bars, each of them represents a well, and that red horizontal line is showing the standard. So another visualization showing, what that distribution looks like with respect to nitrate in this sample data set. Again, to reduce nitrate levels, we want to work to eliminate the contamination source at the land surface. There's a lot of programming going on, conservation programs to encourage things like cover crops, maybe diversifying crop rotations, conservation reserve programs, which are designed to take marginal or underperforming lands out of production and put them into land uses that we would expect or anticipate to leach less nitrate. Those are all things that we should be encouraging to try and remedy or lower nitrate in our groundwater. But even if we're successful, it may take years or longer to notice measurable improvements in somebody's well. So oftentimes we're looking at short-term solutions like well reconstruction or water treatment. Land cover, if we look at land cover, the water quality map is on the left. The agricultural land cover is on the right. So it's not surprising in a lot of the counties that we work in that there's oftentimes a correlation between certain land uses or land covers and what we'd expect to find in the groundwater. The figure on the lower central portion of this divides the wells out by percent agricultural activity within a 500-meter buffer of the well. So when we have 0 to 5 or 0 to 25% agricultural land cover, that generally has a lower nitrate concentration as indicated by those blue diamonds. Those blue diamonds are representing the average concentration for the 124 wells in 2022 and the 148 wells sampled in 2023. As we increase the percentage of land around that well, you'll see that average concentration goes up. Soil drainage is also important for determining this. So we could do the same thing with soil drainage. And I'm seeing that my graphic on the central portion of the figure, the wording is really difficult to read. But the far left graphic would be poorly or somewhat poorly drained soils. And as you go to the right, the soils become more well drained. So if water can move through or drain more easily, nitrate has a potential to move more easily as well. And we do see an increase. As soils drain better, nitrate tends to be more problematic. So that map on the upper right, the different colors correspond to soil drainage, with the red values being the most excessively drained, and the kind of lighter colors indicating some moderate drainage potential. But there's a pretty good correlation between drainage and land cover on our nitrate values. So in terms of next steps, where do we go from here with this information? We'll be putting together a report, but we'll also be doing some additional analysis. We weren't able to complete the analysis for Bering County, so I'm using Chippewa County as an example of how we use the land cover, the soil drainage to create a model that we can then predict nitrate levels essentially on every parcel or any parcel in Bering County. So if we obtain the same attributes, we can then apply that equation to the parcels that did not participate in this program and obtain maps that help paint or fill in the picture of what we might expect to find in other parts of the county where we weren't successful at getting well samples. Or maybe there's just not a lot of wells in those areas to begin with. And we can use these types of tools to gain a better understanding of where we might have problems. Why would we want to know that information? Knowing where we're likely to have elevated levels of nitrate helps for planning, right? If somebody's going to put in a house, they might appreciate knowing what the risk of having nitrate in their well is going to be. It helps us target maybe outreach efforts. If we have limited funding to support well water testing, it maybe helps us focus on those parts of the county where we have one or more issues such as nitrate that we're trying to address or deal with. If we have conservation funding and people are using that funding or applying for that funding, maybe it helps us prioritize which projects or activities are most critical or that we want to tackle first. So this is going to be extremely beneficial to different departments in Bering County, the health department, the land conservation department, as they try to do their work moving forward. So even though only 723 people in Bering County were able to participate in this program, everyone will benefit from the information that we've gained or learned from the well testing that was performed. The other thing we want to highlight is that we have a draft version of a dashboard. So dashboards are online resources that are interactive. They allow you to interact with that data. You can zoom in on the map, not to a level that's going to compromise anybody's individual well or privacy, but it allows you to zoom in a little bit to see what those patterns look like. there's different graphics or figures. And you said that the website, you pulled the website up, correct?
Hit escape out on the. Here.
You have the mouse. See how this works. So this is the dashboard that we have in development for Barron County. And for those of you that participated in this program, just demonstrating some of the functionality that you're going to see. If we click on a well, it does give us a well ID. That's a unique well ID that we assign for the project that is only known to project participants. But it does give you the ability to learn more about the tests, to explore that data in more detail. So if we look at individual wells and we enter, let's say, that well number,
And that's not the state well ID number.
this is not the unique well number that the state provides, correct? This is a well ID that we assign specifically for this project that is only known to myself and the project participants. But you can see if you select that well, it pulls up the individual information for each of the parameters that we looked for. If we were to test in multiple years, we could then add data to this to look at trends over time. So that's functionality that other counties have looked at or pursued, is how do we get some measure of trends, and we do that through repeat testing of the same wells. But if you wanted to look at any of the other parameters, you'll notice all we have to do is select from this drop down, and it'll toggle between many of the different elements that we talked about or discussed. It even includes, if we want to look at the percent agricultural activity around a well, we can click on that and it gives us a sense of what that looks like. Here's some of the other ones. If we're exploring the relationship of some of these different analytes to land cover, maybe soil drainage, you'll see those pop up here. So percent agricultural activity. We even have percent row crops, percent dairy rotation, percent hay or pasture. Here's the soil drainage. Looking at different relationships between these parameters and some other factors that might be of interest. So you can see how you might be able to interact with this data moving forward. There's also this tab that says Learn About Tests. So if you want to know why did we analyze for nitrate, this information talks about what is nitrate, why test for it, how to interpret those concentrations, health effects, and then ways to reduce it in the drinking water, and then strategies to reduce nitrate getting into our groundwater in the first place. So these are the next steps in the project as we're building towards these types of resources or products. How do I get back, Tyler? It's right here. So with that, I'm just going to pull up the last slide. Before we open it up to questions, I am going to turn it over to Tyler or Laura if they have any last minute comments or things that maybe I forgot to discuss or talk about. I'd like to give them an opportunity to add to the conversation. But please feel free if we don't have time to answer your question today or you think of questions moving forward, please don't hesitate to reach out using my email or phone. So with that, again, before we open it up for questions, Tyler, is there anything else that you'd want to add?
No, there really isn't anything. Just once again, thank you for coming. Like Kevin said, the dashboard right now is in draft form. We'll get that established. We'll get that on the county website. I foresee us having on the Soil and Water Conservation Department website, we will have a groundwater section for this information, the dashboard connections. And then for everybody else that didn't participate in this study, places that they can get their own water tested. There are numerous opportunities throughout the state labs for testing, and we just want to make sure that we have that information out there for everybody. Laura Sovi from Public Health has a few test kits if somebody is interested in a nitrate bacteria test, just the kits that will then be sent into a commercial lab. And so those are available out in the hallway. Yeah, so once again, thank you for participating and coming here this evening. And yeah.
That's a long since they took the sample. We directed to take that sample, got a water treatment, in a faucet, do that water.
Correct. We did not want treated water. And so outside faucets are the typical usage.
So yeah, Tyler's correct. We ask that people not treat their water or collect raw water samples. If it was treated, let's say somebody collected from a sample faucet that went through a water softener. We can tell that. We have ways that we know based on the water quality profile that would have went through a water softener, and we'll pull that out of our analysis. If somebody submitted a reverse osmosis sample, that's another thing that we would be able to tell from the results, and we would pull it out of the analysis. It's not that you didn't get useful information from that, but to prevent it from kind of screwing up the analysis, we have ways of screening that out so that it doesn't influence the results negatively. Sure, another question?
So we had our well pump replaced. It's a well pump. The well was 50 feet deep and water. Said the central pivots across the road from 400 feet. And that water was not drinkable. So what's the difference?
So yeah, a lot of times what's more important than spatially where you drill your well on a property is going to be how deep you drill or how deep you case. So there's the total well depth. That's the total depth of the hole in the ground. And then there's the casing. There's that metal pipe that sticks out of the ground, also extends a certain distance below the ground. And that casing is equally as important for determining water quality. Shallow groundwater is going to be more susceptible to what happens on the land surface. It's got a quicker or an easier pathway into that top part of the aquifer. As you go deeper, that well is typically older. And depending on the geology, older water is more likely to contain maybe some aesthetic things like iron or manganese that could potentially make it unsafe to drink. But definitely from a quality standpoint, most people don't like the taste of a lot of iron in their water. So a 400-foot well, if that's the case, that was probably going into really old sandstone or potentially into crystalline rock where we would not, it wouldn't be unusual to find some aesthetic iron, manganese, stagnant water issues associated with it. So I don't know exactly for sure why they said that deep well couldn't be used for drinking, but that's maybe some reason why or what could have caused him to say that. Sure, this gentleman here in the black. So the question was, how should it be used or could it be used to inform future land development? You know, I would think it would be used if let's say we were, someone were building a home or you wanted to build a subdivision, knowing it was in an area of high nitrate wouldn't necessarily prevent somebody from developing that, but you could give people a heads up that if you locate a property here, if you locate a subdivision here, we think there's a high potential of having to need a reverse osmosis system. Or maybe we encourage people to drill deeper in those areas because we know the upper parts of the aquifer are contaminated, and drilling deeper might result in better water. There's other ways in terms of, we talked about conservation programs and being more efficient with how we spend that money to make sure that we're not using that money to perform random, we call them random acts of conservation, where we're just throwing money out there doing conservation, but it really isn't working to improve water quality. If we know where we have problems, strategically targeting our time and our efforts on those areas where there's an indication of problems could also be beneficial from a land use perspective. So when you say commercial products, is there? Sure. Yeah. I mean, commercial developed areas, when we pave over areas, either building a structure or creating parking lots or surfaces, that prevents groundwater recharge. In the winter months, we're probably also salting that. So those types of developments are required to infiltrate their water, but those may be areas where we'd expect to see increases in something like chloride. None of these things are necessarily going to prevent development or discourage development, but they do help us better inform maybe what types of problems or changes in the groundwater we'd expect to see, or what information we could provide to a new homeowner so that 20 years after they've been living there, they don't find out that they've got a particular issue or problem. We had that happen in Kewaunee County where a new subdivision went in, and people were shocked or amazed that they had elevated nitrate levels. We don't want somebody to buy a new $300,000 or $400,000 house and then say they didn't know ahead of time that this was going to be a problem or an issue. It's very easy for us to provide that information. Now that we have tools to help us predict, I think that's what we're hoping to be able to do with some of that, is just better inform people about things like nitrate, or where we might benefit from different landscape activities. So the gentleman in the back, and then I'll come back to you. Okay. Yeah, so every well drilled after 1988 should have a Wisconsin unique well number. That's a 2 or 3 digit letter number code. When I talk about the project ID, that's a 4-digit number that we assign starting with 40, that is unique to this project. If you look at your results, it should be in the comment field. If you look at the comment field, that's your project ID number that you can use with that resource. Thank you for asking that question. So so comment, I'll tell you what, when we provide the information about the dashboard, we'll send results with the project ID because it doesn't look like it was printed on at least your sheet, maybe other people's. Well, we would hard copy, a letter to you, to all the project participants when that dashboard comes out. Yeah. So I'll let Tyler. Perfect. So the question was about pesticides, and really expressing an interest in learning more about the different pesticides or chemicals. What I'll say is pesticides are quite expensive. It's one of the reasons why we didn't include that in the testing for everybody. But knowing, we mentioned how nitrate is a good proxy for land use impacts. Now that we have that, the county is asking what else can they do? And one thing that Tyler and I have talked about is, can we select a subset, maybe it's the highest nitrate wells, and do some additional testing like pesticides on those. You mentioned glyphosate, so I'll provide some additional information on pesticides that I think would be valuable or beneficial, because that's a question that comes up a lot. The Department of Ag, Trade, and Consumer Protection does an extensive testing or survey of wells every 5 years. They look for probably 100 different compounds. They're trying to assess the prevalence and occurrence of the different chemicals that are approved for use in the state of Wisconsin. As widely as glyphosate is used, it does not get into groundwater readily, if really at all. Their testing, even at edge of field wells, doesn't show it migrating into groundwater. It binds to soil, it photodegrades, so its mobility through the soil into groundwater is pretty limited. That's not to say I'd want to drink the stuff. It's not to say I'd want to spray the stuff on a regular basis. Not to say that we wouldn't expect it to find that in our surface waters, because if it binds to soils and we have erosion, that's how it's being transported. We just don't typically find it in the groundwater. If people are going to do pesticide testing and they're going to spend the money, that money is much better spent looking for compounds that we call metolachlor, alachlor, or atrazine type pesticides. Those are the most frequently detected. Atrazine is the one that's most likely to exceed a health-based standard. But those particular compounds, if you're just concerned if pesticides are getting into your water, those are the ones that you're most likely to find, and you're going to get the most value for your money. So as widely as glyphosate or Roundup is used, that's the first question I oftentimes get. But we don't want people to waste their money either. And we have good research to suggest that it's not generally a groundwater concern. But here's some other compounds that you might want to look into. And that's part of the conversation that we've been having, is how to move forward, how to utilize this. So comment about what else can we do with this data? If we combine it with some of the health metrics or health data that we have, can we see some of those patterns? That's an excellent suggestion. No, it can be. I mean, the density. Oh, thanks, Tyler. Yeah. So the question was about septic systems, and can there be issues of people all being on private wells and individual septic systems in close proximity? And the answer is yes. So fun fact, every human excretes about 10 pounds of nitrogen per year. So if we have 2 to 3 people per home, that's about 20 to 25 pounds of nitrogen per year that leaches into the groundwater. If we look at a cornfield, it's about 32 to maybe 70 pounds per acre of nitrogen that we would expect to leach. So if we compare a septic system drain field to an acre of corn, you might assume they're equal, but one septic system on a 40-acre parcel is not going to have the same impact as, let's say, 40 acres of corn. If we wanted to equate the two, we could have a high enough density to essentially make those equal, but we'd be talking about lot sizes of about 0.6 acres or less to have the same impact. For septic system density to have the same impact as a cornfield, that's the type of density that we'd be looking at. That's not to say that larger lot sizes, your well couldn't be located, or it could be located down gradient to where you're noticing a more concentrated impact. But density does matter, and how close we put people on individual private wells and septic systems is a consideration for things like nitrate, but also things like PFAS, which seem to show a correlation to wastewater treatment systems or drain fields. All the food packaging, waterproof clothing that's treated for PFAS, all of that goes to the drain field and could potentially leach into our groundwater and be another consideration for people in that type of development or situation and setting. Maybe one more question if we have it, and then we can break, let people go enjoy the rest of their evening. But again, we'll stick around as long as we need to after the fact. And we do have one more question from the gentleman here. So the question is, where can you get bentonite to abandon a well? Do you want to answer that, Tyler?
I don't know, because I was going to send you to Barron Supply. I know that the price of bentonite has gone up drastically. We used to, in our department, abandon wells. That was a conservation practice that we could do on our own. We would go out and measure the well, the depth, and we had a screen. There was a procedure to do it. The state code changed, and now a licensed well driller has to close a well. So we're not licensed well drillers or pump installers, so we can't do that anymore. So I don't know what the sources of bentonite anymore. If you're going to be closing a well, it needs to be properly done through a licensed well driller or pump installer.
So with that, I think that will conclude this evening's presentation. I'd just like to thank all of you, not only for showing up tonight, but again, for those of you that participated. The project wouldn't have been possible without you and without the help of Barron County and the county deciding that this was a priority for the county to perform. So thanks. Enjoy your evening and safe travels home.